Okay, let's start. Sorry for the delay. Many thanks for Professor Tang for this introduction on me. It's my pleasure to share our research with participants online. This work is a collaboration with Dr. Xu Wenjie and Professor Yunming Chen. This is outline of my presentation. A short background at first, then degradation and stabilization of high food waste content MSW will be introduced. Then 3 kinds of carbon emission reduction technology will be introduced. In 2020, Chairman Xi Jinping delivered China's commitment to the world. China will strive for peak carbon emission in 2030 and carbon net neutrality in 2060. The dual carbon plan not only meets the challenge of carbon dioxide emission, but also non-carbon greenhouse gas such as methane will be paid attention to. The left figure shows the global man-made greenhouse gas emission between 1990 and 2019. It can be seen methane contributes about 20% of the global emission. Landfill methane is the 3rd largest man-made source of methane emission. As shown in this pie chart, it contributes about 2 to 3% of the global emission. The significance of methane emission due to the factor global warming potential for methane is 28 times less carbon dioxide, as shown in this table. How about landfill methane emission potential in mainland of China? Between 1980 and 2020, 3.3 billion tons waste was disposed in thousands of landfill. From 2021 to 2030, 0.85 billion tons waste will still be landfill at sanitary landfill. Landfill emission potential from such huge amount of waste should be evaluated. There are 2 ways for landfill methane emission reduction. One is landfill gas collection and treatment. For example, the collected methane is used to fuel in power generator. Another way is to place biocover on the landfill surface. The escaped methane will be microbially oxidized into water, so the global warming potential is reduced. Landfill methane production depends on waste composition. The left figure shows the relationship between food waste content and GDP per capita for 20 countries. It can be seen the higher the GDP per capita is, the lower the food waste content. For the country with GDP per capita less than $10,000 US, such as China, India, Brazil, the food waste is the main component with a proportion of over 40 red bases, where the waste in developed countries such as UK, Canada, United States contain less 40% food waste content. Here, 40% is taken as threshold value to classify waste into HFWC waste and low FWC waste. With the difference in waste composition, the following questions are raised. What's the difference in degradation behavior between HFWC and LFWC? What's the difference, any difference in landfill gas generation? Are low carbon emission reduction technologies applicable in China? So let me talk about degradation and stabilization of HFWC waste. This table shows physical component of waste from China and United States. The food waste content of Chinese waste is about 58%, where paper is the main component of United States waste. With respect to chemical component, Chinese waste has higher sugar and water than U.S. waste. The difference will significantly influence degradation behavior. The substance in the flash waste can be divided into air, water, and solid phase. The solid phase contains intraparticle water, degradable solid, and inert solids. After landfill, waste degradation results in solid mass loss, water release, solute generation, and gas generation, and also a significant settlement. A large-size bioreactor experiment was carried out to investigate the degradation behavior of HFWC waste under anaerobic conditions. This is similar to most landfill in China. The landfill cell is 7.5 meters high and 5 meters in square. 91 tons waste was filled and compacted and covered with HDPE and geomembrane. The land cell was overlaid with loading, leachate, and gas collection, and so on. Comprehensive monitoring was conducted and lasted for 6 years. This slide shows the experimental results, including leachate production, gas production, temperature change, and settlement. You can see from this figure, within 2 months, there are 27 tons leachate was collected. The quantity is equal to 30% of total waste mass. After half years, methane generation was observed. I show this figure. Heat generation from initial aerobic degradation result in temperature increase. The 2-month settlement is amount to 37% of initial head of waste pile. On the basis, the experimental result, a degradation consolidation model was developed to simulate multi-couple process at landfill. Governing equation involving biochemical degradation, skeleton compression, liquid flow, gas transport, and solute transport were deduced. Numerical solution was achieved on a platform open geosys. During the calculation, the change of constitutive relationship induced by solid mass loss are considered. The material property will be updated in each iteration step. The newly developed model was verified by the large size bioreactor experimental presented before. The numerical result in term settlements, nature production, VFA concentration, gas composition basically represent the experimental results. The theoretical model was used to simulate the stabilization process. A one-dimension model with 10-meter height with power was investigated. The table shows the contents of degradable component put in the model. It can be seen the LFWC waste has much more degradable contents than HFWC. The mass fraction of faster degradable matter in HFWC waste is significantly higher. The parameter of biochemical degradation input in the model are the same for HFWC and LFWC. The red figure shows the calculated hydrolysis degree was 10. In the first 2 years, 80% degradable solid mass is hydrolysis by HFWC waste are only by LFWC waste. This figure shows the calculated methane generation degree was 10. Methane generated after a relief initial acid inhibition. After half years, gas generation start. For HFWC, with the methane generation degrees reach 60% within 2 years, where it takes more than 5 years for LFWC. This figure shows calculated consolidation degree was 10. For HFWC, with over 90 consolidation can be achieved within 1 year. In well drainage condition is achieved. However, it takes 20 years to complete 90% settlement for LFWC waste. This figure shows the calculated degradation stabilization index beta was 10. The calculation of beta value determination of the ratio of cellulose and lignin from flesh and column waste. For HFWC waste, it takes 2 years to achieve 60% of stabilization. For LFWC waste, more than 5 years are needed. We put all the 4 curves together in this figure. The figure includes the measurement of beta value from different from the waste sample taken from different landfill sites. Based on this figure, the stabilization process of HFWC waste landfill can be divided into 3 stages. Include there are rapid degradation stage, slow degradation stage, and post-stabilization stage. The rapid degradation stage takes 2 years, during which about 80 intraparticle water was released, about 60% gas generation potential released, over 80 compression complete in 2 years. When the beta value is exceeded 0.6, the landfill is based slow the degradation in terms of gas generation and settlement. It generally takes about 20 years to reach the post-stabilization stage under anaerobic condition. Based on the understanding of degradation behavior, a new gas generation equation was proposed for HFWC waste. The equation considers the difference between rapidly and slowly degradable waste matter. The parameter for wet and arid climate was determined by gas extraction test listed in this table. This figure shows the calculation of gas generation at the Zhejiang landfill, blue line. A similar scale landfill in Canada is used for comparison with black line. It can be seen at Zhejiang landfill. Massive landfill gas is generated before landfill closure at this time. After closure landfill, a sharp decrease in gas production was observed. But for Canada landfill, the gas generation process lasts for about 60 years. With the calculated gas generation, the equivalent carbon emission potential for landfill waste can be evaluated by this equation. The total ECEP is equal to 1,900 kilograms per ton of waste. It is a big value, nearly twice the total mass of waste. This is due to the very high global warming potential. If landfill is equipped with gas collection and power generator, the ECEP will decrease as a result of methane combustion and electricity generation. The reduced ECEP can be evaluated by the second equation. This table shows ECEP corresponding to different landfill gas collection rate. If 90% of gas is collected and recovered as energy, then the ECEP will reduce to 330 kilogram per ton of waste, only 70% of the total potential. The landfill methane generation in 2021 and 2030 in China can be predicted. The quantity is between 49 to 66 billion cubic, being corresponding to 0.9 to 1.2 billion tons carbon dioxide. It should be noted about only about 75 from the waste landfill for the next 10 years. Only 25 from the waste field from the last 40 years. Now let's talk about carbon emission reduction technology. The first one, based on the identification of three stabilization stages at HFWC landfill, a strategy was proposed for landfill at rapid degradation stage. Landfill gas collection and methane recovery should be implemented. During the slow degradation stage, it suggests to put ecological soil cover on the large sanitary landfill. Aerobic treatment is done on a small, simple dump. Landfill mining can be done at waste at a post-stabilization stage. During the rapid degradation stage, the landfill is generally flooded with leachate. The liquid gas interaction at the wet landfill is quite strong. Landfill gas trap tend to be entrapped under leachate level. Accumulation of gas pressure develop. This figure shows mixture of leachate and gas eject from a well drilled down to the intermediate soil cover. This figure shows field observation of high leachate amount. In addition to high leachate production, another reason for high leachate level is the clogging of drainage system at the bottom. The main leachate level was measured about 30 to 60 meters at two represent landfill located in plain and valley. The high leaching level resulted in a lower gas collection efficiency. As shown in this figure, the green color, the gas collection rate at most of landfill in China is less than 40%, significantly less than that in United States and European countries. The exception is Shenzhen landfill. It will be further discussed later. In order to promote gas collection efficiency, three-dimensional drainage systems are designed to drop down leachate level. The system made of drainage trench and deep well for leachate and gas extraction. The system is able to separate downflow of leachate and upflow of gas properly. In addition, an enhanced temporary cover is implemented on the landfill surface. The system is made of HDP geomembrane underlain by gas collection pipe. 90% of sealing rate can be achieved by this enhanced cover. The combined use these two measures at Shenzhen landfill result in dramatic increase of landfill gas collection up to 90%. The electricity revenue is 37 million Chinese yuan per year. The carbon emission reduction is more than 8 million tons. Solar application at Hangzhou landfill resulted in a substantial decrease in methane concentration on landfill surface. It means the methane emission dropped down substantially. As mentioned previously, ecological soil cover is suggests use on the largest sanitary landfill at a slow degradation stage. Professor Charles already present the working principle in detail. This generally consists of 3 layers, including vegetation, fine-grained soil layer for water storage, coarse-grained layer for capillary barrier. Another more permeable layer is only needed in humid carbon emission can be reduced by microbe-induced methane oxidation layer. The water storage capacity of soil cover can be increased by capillary barrier effect. The effect in fine and coarse-grained soil interface was reproduced by microfluidic technique in our laboratory. This picture shows a significant time lag for the wetting from breaking through the interface. High water saturation was achieved in fine grained layer. The field measurement at the Zhejiang landfill demonstrated the water storage capacity of the cover increased by 40% as compared with the single layer of loose cover. The 2 years field monitoring showed that the Asian monsoon climate is very favorable for the performance of this cover because rainy season coincides warmer season and also plant growing, so it can release infiltration water. The water content at the bottom of the last layer keep over the value of field capacity at most time. The increase of water storage resulted in a decrease in gas permeability by 5 orders of magnitude at most. As there much vapor and heat supply from the wet landfill, field evidence showed there are favorable effects on performance of soil cover. For example, vapor supply does a favor to plant growing at the dry season. Heat supply does a favor to the microbial induced methane oxidation in winter. 50 set our test was performed to measure surface methane emission on temporary soil cover at the Zhejiang landfill. As shown in this picture, the landfill is 2,000 meters long from the upstream to downstream. 50 set of points distributed on the waste pile with different field ages, ranging from 3 to 10 years. The red figure shows the structure of temporary soil cover. With the measured surface flux, both methane and carbon dioxide, the methane oxidation rate can be deduced. Literature review is assumed in oxidation process, 45% methane is converted to biomass, and 55% methane is converted to carbon dioxide. Then the flux of methane at the bottom of cover can be determined, and the oxidation rate can be calculated. The left figure shows the surface flux of methane measured at 50 test points. The methane emission at 80% of test point is less than the limit required by Australia. The red figure shows the fraction of methane oxidation occurred in soil cover. The red line, the fraction is over 60%. It means 90% of methane is transferred into carbon dioxide. Okay. Two types of ecological soil cover strategy have been put into national standard of China. One is capillary bare cover used in arid and semi-arid area. The other is composite soil cover used in humid area. For the last one part is aerobic treatment and landfill mining. Aerobic treatment at wet landfill involve 2 procedures. One is drop down leach level, another one is air injection. After leach drop down, the gas permeability increase, so air can inject into landfill to create aerobic environmental. So the methane generation stop. It's estimated aerobic degradation can reduce carbon emission potential by 16%. The aerobic treatment, waste pile can be excavated screened and reused. The waste are split into three parts. Lighter material such as plastic or textile can be used for power generation. The second, coarse aggregate can be used in embankment fill material. The last one, fine fraction, rich in fumes, but the contents of heavy metal exceeds limit. It should be treated and used for garden and forest. Carbon emission reduction and ecological benefit are not for landfill mining. The technique is implemented at simple dump in Wenzhou City. 750,000 tons waste was excavated, screened, and reused safely. So I don't have time to read the summary, so I can share later. Thank you very much for your listening. Thank you for the invitation from Professor Tan and Professor Shi of Nanjing University. Thank you.